Hello! In this lesson we're looking at triangle congruence, angle, angle, side, and hypotenuse leg. Essential question: what does the angle, angle, side, and hypotenuse leg triangle congruence theorem tell you about triangles? Theorem 4.5, angle, angle, side, AAS congruence theorem. If two angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of a second triangle, then the two triangles are congruent. In our case over here, if angle A is congruent to angle D, and we know they're congruent because they both have one arc, and angle C, which has two arcs, is congruent to angle F, which also has two arcs, and side of line segment BC is congruent to line segment EF. Notice that they are in the same position over here, so they're corresponding sides. Then triangle ABC is congruent to triangle DEF using the angle, angle, side congruence theorem. And we know it's angle, angle, side because I have two angles and a non-included side. Notice that this side is not between the two angles. Then I am using the angle, angle, side congruence theorem. Proving triangles are congruent. We are given that line segment WY is parallel to line segment XZ. This is important information because when I have parallel lines cut by a transversal, I can use angle relationships to prove that angles are either congruent or supplementary using alternate interior angles, alternate exterior angles, corresponding angles, or same side interior angles. I'm also given that angle Y is congruent to angle X. I need to prove that triangle WYZ is congruent to triangle ZXW. Plan for proof. You are given that angle Y is congruent to angle X. Use the fact that line segment WY is parallel to line segment XZ to identify a pair of congruent angles. So let's start by writing down what we're given. We're given that angle Y is congruent to angle X and line segment WY is congruent to line segment XZ. Since I have parallel lines, I can say that angle YWZ, which is this angle over here, is congruent to angle XZW, which is this angle over here, and that's using the alternate interior angles theorem. If you notice, that makes that letter Z over there. I also notice that this line segment WZ is shared by the two triangles WYZ and ZXW. So I can say that line segment WZ is congruent to line segment WZ because I know that this measure is going to be the same for both triangles. I now have three pieces of information. I have two angles and a side, and I notice that this side is not between the two congruent angles. So in this case, I can say that triangle WYZ is congruent to triangle ZXW using the angle, angle, side congruence theorem because I have an angle and a side congruent to an angle, and a side that's not between the two angles. Theorem 4.8, hypotenuse-leg HL congruence theorem. If the hypotenuse and a leg of a right triangle are congruent to a hypotenuse and a leg of a second right triangle, then the two triangles are congruent. Meaning, if line segment BC is congruent to line segment EF, which is the leg of a right triangle, and line segment AC, which is the hypotenuse of a right triangle, is congruent to line segment DF, which is the other hypotenuse, and you have a right triangle, then you can say that triangle ABC is congruent to triangle DEF using the hypotenuse-leg congruence theorem. Proving right triangles are congruent. The pole holding up one end of a volleyball net is perpendicular to the plane containing the points W, X, Y, and Z. Each of the lines running from the top of the pole to X, Y, and Z uses the same length of rope. Prove that triangle VWX, triangle VWY, and triangle VWZ are congruent. We are given that line segment VW is perpendicular to line segment WX, and line segment VW is perpendicular to line segment WY, and line segment VW is perpendicular to line segment WZ. We're also given that line segment VX is congruent to line segment VY and line segment VZ. Prove that triangle VWX is congruent to triangle VWY, congruent to triangle VWZ. To start, I'm going to redraw my three triangles. So I'm going to separate these three triangles so I have better information about it. So here are my three triangles that are broken apart so I can see each triangle separately. I'm given that line segment VW is perpendicular to line segment WX and line segment VW is perpendicular to line segment WY and line segment VW is perpendicular to line segment WZ. That's a given. Because they are perpendicular, I know that angle VWX, which is this angle over here, and angle VWY, which is this angle over here, and VWZ, which is this angle over here, are right triangles, and that's the definition of perpendicular lines. From here, I know that angle VWX is equal to angle VWY, which is equal to angle VWZ, and they're all equal to 90 degrees because that's the definition of right angles. I am given that line segment VX, which is this line here, is congruent to line segment VY, which is that line there, and that's also congruent to line segment VZ. Notice how in each of these triangles they have the same line segment, which is VW in all of them. So all three triangles share the same line segment, which is VW. So I can say that line segment VW is congruent to line segment VW using the reflexive property of congruence, and I'm going to mark this on my triangles. So I now have three pieces of information. I have a leg, a right angle, and a hypotenuse congruent to a leg, a right angle, and a hypotenuse congruent to a leg, a right angle, and a hypotenuse. So I can say triangle VWX is congruent to triangle VWY, which is congruent to triangle VWZ, using the hypotenuse-leg theorem. All right, that's it from me. I'll see you all soon.